Hello everyone, my name is Anubhav Dhar and today we will be discussing the problem The Two Dear Friends of Chefland from CodeNite May 2022. So first let's start by discussing a brief version of the problem statement. So in this problem we are given a tree of n vertices such that the uth vertex has a node weight of v of u and the jth edge has an edge weight of tj. Now we are asked to handle q queries of the form. So there are two kinds of queries. The first kind is of the form exclamation mark u v r. This means that you take the edge from u to v and change its value to r. For example, if we take a query like question mark 2 1 5, you take the edge between 2 and 1 and change that value to 5. The second kind of a query is basically something like question mark AB. This means that of all nodes V such that the path from V to A passes through B. So let's call all such nodes the set of valid nodes. The set of valid nodes is basically the set of nodes such that the path from that node to A passes through the node B, and we choose any vertex V uniformly at random from the set of all valid nodes, and then we compute the value of distance from V to A times weight at node V. So distance of V to A is basically the sum of all edge weights from on the path from V to A. So we report the expected value of this. Okay, I hope the question is clear. So before we dive into the solution for this problem, so we will be assuming that some of the concepts are clear. So the prerequisites for understanding the solution are: we already know how to find LCA, we already know how to use segment tree and lazy propagation on the Euler tour of the tree to get some values over a subtree or update some value over some subtree. With these two concepts in hand, we can dive into the solution. So the first step is to root the tree at node 1. Well, you can root at any arbitrary node. We will be assuming we root it at 1. And once we have rooted the tree at node 1, we can define some quantities as follows. So we define S of u as the subtree of u. So this is a set of nodes. The second definition is capital T of u, which is basically the sum over all nodes V of the quantity distance of u to V times weight of V. So in terms of the problem statement, this quantity basically represents the sum of costs from traveling from all cities V to U. The third definition is C of U, which is basically distance of 1 to U times V of U. So this is the cost to travel from node U to node 1. And then we have another definition d of u, which is basically just distance from between 1 and u. And further we can have another definition such as m of u, which will give us basically the sum over all nodes that belong to the subset of u of the quantity distance of u v times weight of u. So basically this value is the cost, the sum of cost to travel from all cities in SU to city U. Okay, so with these definitions in mind, we can actually come up with a way to handle this. So as I might have already spoiled at the beginning of the solution, so we will be using segment trees on Euler tools to handle most of this stuff. So first of all, let us talk about updates. So updates are of the form exclamation mark u v r. So what this signifies is we have the tree somewhere around here, and then for a particular edge in the tree, so let's assume that this is u and this is v. So u is the parent of v. If not, we can simply swap u and v, and then we change this edge weight to r. So let's say the initial edge weight was small q, and then we are modifying this to r. So the change in edge weight is basically r minus q, and let us denote this by delta. Now when this change is incorporated, let's see how these values change. Well, the subtree of u is basically defined for convenience, and this does not change as the structure of the tree does not change. But let's see how distance from 1 to u changes. So the distance of everything in the subtree of v increases by delta, whereas everything outside the subtree of v remains the same. So for the orange region, the distance changes, whereas for the blue region, the distance does not change. So we can actually keep a segment tree on the Euler tool of the tree carrying this distance value, and then we can only change, we can add delta to the distance value from 1 to v to all nodes in this region, and that will basically do the job. Well, now we know how to handle d of u. Now what about t of u? Now notice that for any node over here in the blue region, let us call the node small a for instance. So what happens is the sum of all other nodes in this blue region do not have any change, any effect to change the value of t of a. So basically we can write t of a as, so sum over all nodes, and let's say we write this as b instead of v, and then we compute this value. So this can be broken down into two parts. B belongs to S of S of V. So this is from the orange portion. B belongs to S of V, so B is in this portion. Distance of A to B times weight of the node B, plus B does not belong to S of V, the same thing. So writing it more rigorously, this will be something of the form: B belongs to the set So this means that B is from this blue region. Now notice that when this edge is updated, this blue value does not change, but the orange value changes, and the change is exactly equal to an increase of delta times the subtree sum of V. So why is this true? So for any node in the subtree of V, so if B is in the subtree of V, so the path used to go from B to V and then V to A, but now the path from V to A goes through this edge, and now this edge has a change of in weight of delta. This means that this distance value is changed to plus delta for all V, and now we can actually take this delta out, and then this will just be delta times weight of V. So for an update, we can just update this part of, so for all A's over here, there will be an update of this. So notice that this does not depend on A. This is a function that is independent of A. So for all A's that lie in the blue region, the new value of PA will just be increased by this value. So this can be done by a lazy propagation update on two separate ranges. So the range that occurs before the start time of V, and the range that occurs after the end time of V. So now this part is done. Now let's discuss what happens if A is from the orange portion. Okay, so now if A is from the orange portion, the same thing happens, but now instead of an increment of delta times B that belongs to S of VW V, so this is basically the subtree sum of V. Instead, for all B that lies in the blue region, you need to travel an extra delta length. For that, you need to add the value of B does not belong to S of V, weight of V. So how do we do this? This is basically subtree sum of 1 minus subtree sum of V and times delta. So now we can update this value we can add this value to this range for all nodes in the subtree of V. Okay, so now we know how to update DA accordingly. So we have discussed DU, we have discussed T, we have discussed that S is basically a mathematical notation and does not require any updates. Now let us discuss how do we update C. Now the update for C is a bit tricky. For time being, let's forget about this problem and let's just focus on a new problem. So in this problem, you are given a sequence X and another sequence capital Y, and you need to find, you are given queries of the form from L to R, find the sum of xi y times yi. This is query, and updates of the form increment xi by some number k for all I in the range L to R. So how do we accomplish this using segment trees? Well, in a particular node, instead of, so we can store basically, so as usual we will be storing the final value that we want to calculate. So this particular node will be storing this value, and with that we would also store the value of summation over yj. So call this to be capital, let's call this alpha, this, let's call this value beta. So now what happens is, when you merge two nodes, so this is alpha left, beta left, this is alpha right, beta right. So alpha is basically the sum of the range that the segmentary node is responsible for of the value xi times yi, and beta is sum of just yi. So for this node, alpha node and beta node, this is simply alpha left plus alpha right and beta left plus beta right, the way things happen in a normal segment tree. Now the catch is, when we wish to update a particular range, we can actually update the value of beta. So beta value is not updated, beta value is never updated, because we only increment xi's by k, and we can update alpha I as alpha n as alpha n plus k into beta n. So basically for all, so if the x, so the updated x is x1 of I, yi, so this is the updated alpha, this will be equal to xi plus k. So this is the xi that we used to have previously times yi. So this will just be equal to this part times this part, which will be the previous alpha n, plus k into this part, so which will be k plus beta n. So now we know how to do this, and we can use lazy propagation to update these values of alpha lazily. Now we will be using this kind of a data structure to handle the updates in C of U. So how will we do this? So whenever there is an update from U to V, the value of C of B for C of, let's say, A, for some node A, which was equal to distance from 1 to A times B of A. This value changes only if it's in the orange portion. Obviously the path from 1 to any node in the blue portion does not contain this edge, and hence the value remains unchanged. Now how does the value over here change? So the new value over here changes by distance from 1 to A. So this is the old distance plus delta times WA. Now the catch is, this is what we were calling X of A, this is what we were calling K, and this is what we were calling Y of A. So over here you see that you want the sum over xi times yi over a contiguous range. Here also you want the sum of xi times yi for some range. And further you can update some values of x by increasing it by k for a contiguous range, and here also you are increasing the value of c, so for the value of xa by a particular value k, which is equal to delta, for the contiguous range representing the subtree of v. So now this can also be handled by a segment tree that can take care of these operations. Okay, that means that we can now handle C of U, we can handle P U, and for MU is basically MU is basically equal to sum over, let's say, so V belong to S of U of the value distance from U to V times W of V. Now instead of this distance we can write it as, so okay, let's not make it U comma V, let's keep it A and B. So for this it's simply equal to, so this part I can actually write it as distance of, so d of A minus d of B, rather d of B minus d of A. So distance from 1 to B minus distance from 1 to A. And since B is a subtree of A, B is an element in the subtree of A, the distance from A to B will be exactly equal to the distance from 1 to B minus the distance from 1 to A. Okay, so this can be simply written as this minus distance of A times weight of B. B is in the subtree of A. So this part is basically a range query on C. This is basically, instead of db wb, we can actually write cb. So observe that cU is basically equal to, So this is basically equal to d of u into wu. So this is a range query on B, and this is the subtree sum of A multiplied with the depth of A. So this can also be taken care of. So everything from T to M can be taken care of, that is, it can be updated in order logarithm of n time. So updates are of order log of n. Now moving on to queries. So queries are of the type question mark AB. Now we can actually divide this queries into three cases. So first case is very straightforward. It's a case that A is equal to B. The second case is that A is not in the subtree of B, and in the third case it's A is in the subtree of B. So let's handle the first case. And again, I'll be reminding you the definition of valid node. So any node is called valid if the distance from if the path from that node to A goes through B. So we will call these nodes as valid nodes. So in the first case, where A is equal to B, we can have something like question mark 3 3. Whoops. Yeah, okay. So in a query like this, we can have something like question mark 3 3. This implies that the set of valid nodes is basically the entire set of nodes. So it's from 1 to n. This means we need the value of expectation. So this means that the needed value of expectation is basically the sum over all nodes distance from V to A times weight of V by n. This is basically T of A by n. So if you remember that T was defined as the distance from U to V over all V times weight of V. So this case is quite straightforward. The next case we have is A does not belong to the subtree of. So this means that there is B somewhere and A is not over here. A is somewhere over, let's say, here. So in other words, the LCA of A comma B, let's call it L, is not equal to B. Now if you observe closely, the set of valid nodes is the entire subset is in the entire subtree of B. So for any node in the subtree of B, this must go through B before making it to A. And for any other node that is not in the subtree of B, this won't pass through B. Hence, our required answer will be the sum over all V such that V is in the subtree of V of the quantity distance from V to A times weight of V. Now, how can we exploit the definition that we had to get this value? So in this case, we can actually break this down into the following. We can actually break this down, break the distance from V to A as distance from V to B plus distance from B to A. So this can be written down as sum over V is in the subtree of B, distance of V to B times WV plus summation over V belongs to S of B, distance of B to A into WV. Okay, now if you remember that this is some quantity we know. More specifically, this is equal to M of D. Remember that M of U is equal to V belongs to the subtree of U, distance from V to U times weight of U. So this is actually equal to M of D, whereas this value can be written as, so this can be written as D of B plus D of A minus 2D of L times sum over sum of WV such that V belongs to SP. So this is basically subtree sum. This can be pre-computed easily. So this gives you the final answer. Now for expected value of this thing, we should divide this by the number of valid nodes. So what is the number of valid nodes? Well, it's the size of subtree of V. So the final answer would be something like MB plus DB plus DA minus 2 into D of L into subtree sum of V divided by size of SB. So which can be also pre-computed at let's say subtree size of. So this gives us the final answer. Now let's talk about the third case. A belongs to the subtree of B. So the tree looks something like you have B and you have some children of B, and then you have E inside the subtree of B. Now first let's identify the set of valid nodes in this configuration. So if we observe closely, we find that if we define E as the child of B such that, let's say, parent of P is equal to B and A is in the subtree of this particular child of B. So A belongs to the subtree of B. So you notice that everything that is not in this green region is a valid node. So for example, any node over here that is under this subtree, and you take the path from this node to A, this will pass through B. Again, for any node that is entirely outside the subtree of B, this will also pass through the node B before hitting A. So basically the set of valid nodes is mathematically equal to the set of all nodes minus the nodes in the subtree of P. Okay, this means that this number of valid nodes is equal to n minus subtree size of okay. So let us start by writing the sum over all costs from all valid nodes to A. So the sum that we want is basically from the set of all valid nodes, that is from 1 to n except the nodes that are in the subtree of P, of the value of distance from V to A times W of V. Now since the nodes are not in the subtree of P, the path from V to A must pass through P. Hence we can write this value as distance from V to P plus distance from, I think I need more space, plus distance from P to A times weight of V. Okay. Now we can further break this summation into two parts. V is from 1 to n distance of Vp times weight of V plus distance from P to A weight of V minus the values of these when summed on the subtree of P. So we have included the subtree of P in these summation over here, and now we need to deduct those. Distance from V to P times weight of V plus, so the entire thing is negated, distance from P to A weight of V belongs to S of P. Now notice that this quantity is basically equal to T of P. This quantity over here, this is simply equal to distance from P to A times subtree sum of 1. Right, subtree sum of 1 means the sum of V of W of V over all nodes. Since the tree is rooted at 1, every node belongs to the subtree of 1. Minus this value is basically equal to M of P. Right. So for all nodes in the subtree of P, we are finding the distance from V to P times the weight of P. Whereas this value over here is simply equal to distance from P to A times subtree sum of P. So this is the sum of all costs over all valid nodes, the entire thing. Now notice that distance from P to A can be computed in logarithmic time using binary lifting, that is with LCAs and all, and hence we get our final answer as this value, distance P to A times subtree sum of 1 minus MP minus distance from P to A, sub-tree sum of P, divided by the set of valid nodes, which is basically n minus sub-tree sum. Hence, we have solved the problem for all three queries. And since we can handle the updates over all these in logarithm of n time, and we notice that all operations that were used to answer these queries, so over here we need sub-tree sum and MB, and over here we need TP, MP, and sub-tree sum and distances, and over here we need TA. All these things can be found in logarithmic of n time. So the entire problem can be solved in q log n plus n log n. So this completes the discussion on the solution of this problem. So if there are any problems, please let us know in the comment section. Okay, thank you.